Hello everybody. Today I'm going to talk about a quite interesting trick I found out while I was solving some harder disjoint set union problems. Now let me briefly introduce what disjoint set union is, also shortened as DSU. So, given some sets, let's say the set of numbers from 1 to n, we can do some we can run some queries. Uh, the first query would be to unify some sets if they are not already unified, like basically adding some edges in a graph. And the second query would be to find whether two numbers are in the same set. As you can see, this can be done with DSU, and basically we are going to keep two arrays where we basically have that that I is basically the root of the set uh, where I belongs, and rank of set I is the cardinal of the set, like how many numbers are in the set. At the beginning, that I will be equal to I, and rank I will be always 1. In order to run DSU, we will need to implement two functions. The first function will be a union function, which basically unifies two sets, and the second one is function find, which for a certain node finds who his root is. In order to implement this effectively, we need some optimizations. In the find function, basically we need to compress the routes in order to avoid calling the same function more times that it actually requires us to do it. Like, we need to write something like this. Basically, if we found the root, we are going to stop. Otherwise, we are going to assign the value of the function for its dad to the node. This is a quick implementation of the function find. I know it can be done iteratively, but there isn't a big difference in runtime when implemented recursively. Now let's move on to the union function, which basically unites two sets if their root is different. Uh, we can implement it as a void function, where as the parameters we will get the two sets, represented by some numbers belonging to those sets. Some people prefer to do the checking whether A and B are in the same set here. Other people prefer to do it in an if before calling this function, but I will write the check anyway. Basically, we need to find out whether the roots of the set A and B are equal. Using the function written previously. If this happens, we can't unite anything. In order to do the implementation easier, we are going to always unify B to A. But in order for this to actually be effective, we need to unify the set with the smaller cardinal to the set with the bigger cardinal in order to avoid too many calls of the function find. If rank of the set A is smaller than the rank of set B, then we are going to swap. And here we are just going to append the set B to the set A. Set of the set B. Oh, actually, rank of find A. Excuse me. I think I'm going to write again. We are going to firstly make them equal to their roots. If A is equal to B, we are going to stop. Otherwise, if rank of set A is more than rank of set B, we are going to swap A and B. And we are going to unify the smaller set to the bigger set, which can be written like this. Instead of set B becomes A, instead of being its own root. And the rank of the set A is added with the rank of set B. This allows us to solve multiple problems which involve offline connectivity. Like if we have all the queries beforehand, and let's say we're asked to find if two nodes are connected, we can use disjoint set union and either run DS2 in the order of the given edges or in the order in the reversed order. Another application of disjoint set union will be Kruskal's algorithm for minimum spanning tree, but this is a discussion for another video, since I'm going to focus on the actual trick which I was going to present. Now let me briefly introduce a problem. Let's say we have a graph of n nodes. In this case, n will be quite small, let's say 6 nodes. And we have some queries. One query is to find out after how many edges will nodes A and B will be connected with A different from B. One update, add one edge. And query is, as I said, when A and B will be connected. And yes, you can say now that, hey, we can solve it with parallel binary search. But it sounds complicated, right? Yes, it actually is quite complicated. But fortunately, there is a solution using disjoint set union, assuming we can only add edges and not remove them or do other stuff. Now, for each number from 1 to n, we are going to keep some numbers which involve the number of the queries involved with this number. Let's say we have uh, queries like that: 2, 5, 1, 6, 1, 4, 2, 3. And they are first, second, third, and fourth query. And let's say at the beginning we are going to append to each of 2 and 5 number 1, which means that number 2 has one half of the query 1. For the second query we have 1 and 6. For the third query we have 1 and 4. And the fourth query will be 2 and 3. So basically the numbers here will mark how many halves of the queries we already have. Now, let's say we are going to unify 6 and 3. We are going to draw an edge, and the resulted set will have one half of both query 2 and 4. Now, let's say we are now adding 2 and 3. 2 and 4, excuse me. Now, the resulted set will have one half of queries 1, 3, and 4. Now, let's say we are going to add 1 and 6. Since the set has 2 and 3, and also 2 and 4, we can observe that we have 2 in both halves. So what we are basically going to do is to mark the fact that we got 2, like the answer for the query 2 is 1, 2, 3. Like we had to add 3 edges in order to have the nodes in the query 2 connected. And we are going to delete both operations of 2 in the set. This can be done with set from C++. Now let's say we are also going to add an edge between 2 and 3. Now we have 3, 4, 1, 3, 4. Both 3 and 4 will be united. So for both queries, the answer will be 4. And we are also going to delete them from both sets. And as you can see, we are left with just one. And let's say if we add the edge 5, 4, we are finally going to have the query 1 completed, which will be answer equal to 5. Yes, it seems quite interesting, but we can also solve more complicated problems. Like, let's say we have some costs on the edges, and we have a special definition of the cost of a path from node E to node J. Let's say the cost is the value of the maximal cost on the path from I to J. We can also, if we have such queries, we can also find out using this algorithm and sorting the costs of the edges beforehand, which is the cost of a path from I to J. I'm not going to solve that problem because it's quite similar to this one, but I'm going to focus on the implementation details. Basically, what we are going to do is to keep another array where of I is where are we going to store the values for the set I. At the beginning, this will be also initialized like the dead one with 1 to up to n, and we are going to keep some sets. It can also be done with arrays if you have simpler kinds of queries. Let's say n plus 1. In a set, we can keep one half of the query. And now we are going to modify just the function union. In the sets, we are going to have the nodes, the halves of the queries, basically. In the onion union function, basically, we are going to do everything like in the previous function, same as basic. But before we actually unify the set, let's write at least a equal find of a, b equal find of b. After checking if the sets are the same, we are going to find out the sets corresponding to a and b. Let's say int c equal where I think I called it, where of a, and int d equal where of b. Now we are basically going to do the same for the set C and D as we are going to do for the A and B. We are going to add the smaller set to the bigger set and basically check out for all the elements from the smaller set if the other half of the query is in the other set. Why does this work? Because we are going to unify two sets and the answer can be modified only if one half of the query is found in both sets. And it's faster to check the smaller set and then do some binary search in the bigger set than do the other way around. Let me explain, and this is also same as basic, but now let's focus on unifying this. Basically, when we are going to unify two sets, we are going to check for each half of the query if it finds out in the other set. This can be done with an iterator in case of set. Uh, let's say S of D. We will assume again that set D is smaller than set C. And we are going to check if we find in the set C the iterator. And X equal to lower bound uh, IT, and if IT is equal to X, we found the answer for that query. Otherwise, we are going to keep in some array. The values which were not added. Yeah, it's as simple as that. And at the end, we are going to insert all the elements from the vector in the set. Insert all of V to set C. And again, we are going to unify those sets. As you can see, this trick can solve quite a hard problem, which involves connectivity, but in an easier version. With, and it is quite easy to implement compared to the parallel binary search method. I haven't seen this trick too often. I mean, the only problem I can recall is a Romanian problem from the National Olympiad in Informatics from some years ago. But I'm quite sure that there are also other problems which can be solved in a similar fashion. You can write this in comment, like if you find similar problems. And I also invite you, if it exists, to write the name of this trick, since I don't know if this trick is actually well known or not. And I invite you to write if this trick actually has got a name. Now, uh, thank you for watching. You can check out the description, and if you like the video, please like it, subscribe to my channel, and join the Discord server where we can talk more. Until the next time, stay healthy and bye.